Scientists are brushing up upon age-old questions that used to be the purview solely of theologians.
Last century, a radical idea about the origin of everything was born. It would become the most famous theory in all of science.
Fred Hoyle, in a rather derogatory way, described it as a Big Bang.
As the Big Bang theory evolved, it made predictions that were only confirmed by accident.
This radiation was discovered using this radio antenna that wasn't even looking for it.
What was coming out of this thing had to come from somewhere.
Had science discovered the moment of creation?
We're looking at the infant pictures of the baby universe.
But the Big Bang theory had its challenges.
There were several problems that could not be explained without conspiracies.
Cosmologists were forced to propose a mind-blowing scenario to fix the difficulties.
I wake up my wife and I said, I think that I know how the universe was born.
They claimed that the universe expanded by trillions of times in a tiny amount of time. An idea called inflation.
It took the observable universe and flung it apart so fast that space itself expanded faster than the speed of light.
But could this be true? Or was there a flaw in the whole idea of the Big Bang itself?
There should be a telltale signature all over the sky.
An intrepid team of scientists built a telescope in one of the most inhospitable places on Earth, looking for the answer.
It could be one of the greatest experiments of all time.
But the team would face intense challenges and controversy as they battled to answer the greatest scientific mystery of them all.
So, is the Big Bang right?
Wondering where the universe came from is the biggest question anyone can ask. All the billions of galaxies, the untold trillions of stars and planets, stretching out over unimaginable distances, what could possibly have made them? For some, the question itself was irrelevant because the universe never had a beginning. It had just always been.
Well, our lifespans as humans are very short compared to the age of the universe. So during our lifetimes, the universe doesn't appear to do very much. If you couple that with people's limited ability to observe distant objects, the universe did appear very static.
But for others, a moment of creation better fitted their beliefs.
There was a persistent belief that the universe must have been created as we see it, and generally that was attributed to God.
Yet other religions believed that the universe might be an everlasting cycle of birth and death.
These ideas that humans have had about whether there's a beginning to everything or something that's more cyclical, that is everlasting, that didn't have a beginning, that didn't have an end. These are things that are absolutely reflected now in the questions that we're asking, now that we actually have data and we're kind of doing this from a scientific point of view, not a religious point of view.
Most scientists at the start of the 20th century thought the universe was static and had always been. But in 1915, preconceptions about the origins of the universe would be challenged when Albert Einstein published a paper.
He came up with this beautiful theory of general relativity, which tells us how the whole of space-time should behave. It tells us that if you put mass into it, a bit like throwing a ball onto a rubber sheet, it deforms space.
At its core, general relativity said that neither space nor time are rigid. They are continuously distorted by matter. But Einstein was troubled by the implications of this on a cosmic scale.
He came to realize that his new theory of relativity said that space actually should be changing. If you just put masses into space, the gravity of them should actually try and pull the space between them back together and should actually shrink space. But Einstein hated this idea. Einstein thought that the universe was static. And so he came up with this thing that he called the cosmological constant.
So Einstein's cosmological constant is a kind of a fudge factor that he inserted into his equations. And he did this really just on grounds of prejudice. You know, towering genius that he was, he somehow felt compelled to fix his equations to prevent the universe from expanding or contracting.
In 1922, a Soviet scientist called Alexander Friedmann began corresponding with Einstein.
He was sort of inspired by Einstein's new theory of relativity and tried to apply them to the whole universe.
And, you know, he quickly realized, as Einstein had, that the natural behavior of such a universe was to expand or contract, and that being perfectly stable was a kind of vanishingly unlikely knife-edge point between those two possibilities.
He said, depending on the kind of initial conditions, depending on how you started things off, space could be growing. But whatever it is, it shouldn't be static. It shouldn't be unchanging. And so he wrote a couple of scientific papers, but Einstein didn't like it.
It wasn't long before others would challenge Einstein's position. Working independently of Friedmann was mathematician and priest Georges Lemaitre.
Lemaitre was a very remarkable man. He had a distinguished war career. He was awarded the Croix de Guerre by the King of Belgium for his service in the First World War.
A few years after Friedmann, he took a step further. He said, well, if the universe is indeed growing, then it must have come from somewhere. It must have had some beginning. He called it a cosmic egg.
Lemaitre was the first to suggest that the beginning of the universe would also be the beginning of time.
He called the beginning of the universe a day without a yesterday.
Einstein, when hearing about this for the first time, called Lemaitre's math elegant, but his physics atrocious.
But Lemaitre had an ace up his sleeve.
He also figured out what we should expect to see around us if the universe were in fact growing. And so we should see galaxies moving away from us. And the ones that are further from our Milky Way should recede from us faster than the ones close by.
In a paper published in 1927, Lemaitre had given a prediction of how fast the expansion might be, depending on how far away we look.
Well, this is where the experimentalist comes in, and it always pays to look and let the universe tell us what it thinks.
And Lemaitre was already acquainted with one of the world's greatest astronomers, who was studying the most distant parts of the visible universe.
So Edwin Hubble studied the motion of galaxies, and all the galaxies that he looked around at were all receding from us. And that was exactly the kind of prediction that Lemaitre would make, that the universe would be expanding.
In 1929, Edwin Hubble published his results that concurred with Lemaitre's predictions. The further away the galaxies he observed were, the faster they were moving away from us. He calculated that the most distant galaxies were moving away at thousands of kilometers per second.
Einstein, in fact, visited Edwin Hubble and his telescope here in Pasadena and came to the conclusion that putting in this cosmological constant was a mistake, and accepted the idea that perhaps, this was possible. The universe is actually a dynamic place, expanding from a beginning time.
It was rapidly proposed, what's going on? It's not that there was an explosion centered on our galaxy. It's just that the entire fabric of space itself is expanding. If you think of such a picture, a kind of expanding grid with the galaxies on the grid points, it turns out that every point, as it looks out to other points, sees all the points receding. It doesn't matter where you are. Every point is the center of the expansion, as it were, and the galaxies are just being carried along in the flow of the expansion of space.
Now that most of the world's cosmologists believed that the universe had a definite beginning, they could start to figure out how it might have worked.
Scientists began to develop ideas about what should happen in these very hot conditions in the early universe.
I think the biggest advance was by a fellow named George Gamow. He and his collaborators looked at the possibility that elements were cooked up in the early universe.
And this was called primordial nucleosynthesis.
Gamow theorized that at the very beginning, there was only intense heat and energy. Over the next few seconds and minutes, the energy condensed into the first atoms. But they were incomplete atoms. The baby universe was too hot for electrons to become attracted to the atomic cores.
And so you have this very short window in which you can create cores of atoms, and you just have long enough to do that before the universe then cools down enough that you can't do it, a bit like turning your oven off.
You would only be able to develop very light elements like hydrogen and helium, a little bit of lithium.
And this mixture of elements was then remarkably consistent with what astronomers can actually see now out in the skies around us.
But Gamow and his colleagues also made a prediction of immense importance.
He also found that as the universe expands, it should leave a remnant radiation background.
370,000 years after the beginning, the expanding universe would have cooled down enough for the electrons to become attracted to the incomplete atomic cores.
So the significance of this moment when the electrons and protons come together, which we call recombination, is that not only is the full hydrogen atom formed for the first time, but light rays now travel freely through space, eventually towards us.
And so the prediction was that we should be bathed in this primordial radiation of light rays that have indeed been traveling for billions of years since that beginning of the universe time.
Gamow and his collaborators called this first visible remnant of creation the cosmic microwave background. This entire process of the universe expanding from an ultra-dense, ultra-hot state and forging matter from energy was given its famous and misleading name by a skeptical British cosmologist called Fred Hoyle on a BBC radio program.
In a rather derogatory way, he just described it as a big bang. Well, it caught on like these things do.
When people call it the Big Bang, they almost always picture the wrong thing. They picture a firecracker at a place and a time. What we actually observe is the infinite universe expanding into itself with no actual first moment. People are shocked when I tell them this. We've been told the wrong thing by astronomers and science writers for generations, and it's hard to take the meaning of the words that Fred Hoyle gave us.
If the Big Bang really did happen, then finding the cosmic microwave background that Gamow and his colleagues had predicted became of vital importance.
The challenging thing is that it would be very difficult to find, because as the universe has grown and cooled down, this light from the early universe has stretched its wavelength well beyond the waves that our eyes can see into microwave wavelength. And they should now be extremely cold, almost absolute zero.
The temperature of this cosmic microwave background, or CMB, was carefully predicted by a Princeton scientist called Jim Peebles. Some of his colleagues then set about trying to find it.
And then, completely serendipitously, this wonderful thing happened.
When I took a job at Bell Labs, they had a unique radio antenna, which we planned to look at some special things in radio astronomy with. And what we found was something we weren't looking for.
Rather than collecting light that our eyes can see, radio astronomy uses antennas that capture light of much longer wavelengths, like microwaves and radio waves. Only 26 miles from Princeton University, Robert Wilson and his colleague Arnold Penzias wanted to use their radio antenna to measure the emissions coming from the halo of gas around our own galaxy. But in order to do so, they would first need to calibrate it.
Radio astronomers aim their big antennas at a source they're interested in and get a signal, but then they turn them off to the side a little bit, and so they measure the difference between near the source and on the source.
Wherever they pointed their telescope, they always found background radio emission, a kind of noisy hiss at a certain frequency.
The background should have been quite small. And so we had a real conundrum that the antenna was producing more noise than we could understand.
Arno and Bob set about trying to locate the source of the noise that was ruining their experiment.
Yeah, we had a checklist of something like 9 different things, but things like we had a perfect view of New York City. Could it be that the city is noisy and that the side lobes of our antenna were picking that up? Well, we had the perfect instrument. We turn it around and we look at New York City. Nada.
They wondered if the troublesome signals were coming from the ground, and so they wheeled a cart around the antenna with the radio source in it. But again, nothing. Bob and Arno were narrowing down their list. But what if it was something inside the antenna that was causing the problems?
There was a pair of pigeons who had taken up roost in the antenna. They would fly up just about into the cabin of the antenna, and it must have been a nice, toasty place to be.
It wasn't necessarily the pigeons that were suspected of causing the interference, but something they were leaving behind.
There was this white dielectric material all over the inside of the horn reflector, and so we thought it could be radiating. We first got a trap and put it where the receiver normally would be and caught the pigeons. We put them in a cardboard box and mailed them as far away as we could in the company mail to a pigeon fancier in Whippany, New Jersey. Well, he took a look at these pigeons, said, "These are junk pigeons," and let them go. Well, a day or so later, here are the pigeons back. So that didn't work. Our technician brought in his shotgun and in the name of science, dispensed with the pigeons. In short, none of the things we could think of and do anything about actually made any difference.
A hint at where their problems might lie came when Arno had a chance conversation with a fellow astronomer.
He said to Arno, "What's happening with your crazy experiment?" And Arno laid it on him. "We've got this excess noise in our antenna. We can't find it." He said, "You ought to talk to Bob Dickey at Princeton."
Bob Dickey was the colleague of Jim Peebles at Princeton University, whose team were already actively looking for evidence of the radiation predicted by the Big Bang Theory. Although Peebles had calculated what kind of radiation they were looking for, their experiments were only being calibrated and had yet to begin. The team were eating lunch together when the phone rang.
Dickey picked up the phone and they heard atmospheric radiation, sky temperature, antenna noise, all the things they were interested in. Dickey put down the phone and said, "Boys, we've been scooped."
Robert Wilson and Arno Penzias had accidentally found what Jim Peebles and George Gamow had predicted.
We invited them over. They looked at our antenna and all the measuring system and agreed that we'd done the right thing. We went down in the conference room and they told us about how a Big Bang might produce a universe full of radiation.
Wilson, Penzias, and Peebles were all awarded Nobel Prizes for their parts in this momentous discovery.
And suddenly, it changed everything. The fact that we see the galaxies expanding around us, we see the elements in the right abundances that you'd expect from a hot Big Bang, and then we see this radiation coming from all directions in the sky. Those three things became the pillars of the Big Bang theory.
So now scientists had a picture of a universe that expands from a Big Bang, cooks up basic elements in the inferno, and leaves behind a detectable background. But that couldn't be the whole picture.
The hot Big Bang model was on pretty firm footing, but there were definitely some puzzles.
This CMB radiation did appear indeed to be the same temperature everywhere. And that's really weird because you're receiving a ray of light from all different directions, and those rays of light have traveled for 14 billion years to reach you. And they could only have achieved the same temperature if they were once in contact. There was a second problem, which is that the universe seemed to be something known as flat.
The universe is observed to have very close to what's known as spatial flatness. What is spatial flatness? So if you imagine yourself on the surface of the Earth locally looks very flat, meaning that if you go to a sidewalk and you draw a triangle with 3 straight lines to it, you will get, when you sum up those 3 angles, 180 degrees. However, if you make that triangle bigger and you put one vertex of the triangle in Bangkok, one in Mexico City, and one at the South Pole, that triangle has about 270 degrees between its 3 angles when summed together. Now, imagine going off the surface of the Earth, pick 3 stars, measure the angle that they subtend, and make the triangle, and observe their 3 interior angles and add those up. It turns out, no matter how big a triangle you make in the universe, those angles always add up to 180 degrees. So it's very, very striking that the universe was fine-tuned to parts in a billion or a trillion in its curvature right after the Big Bang. How could that possibly happen?
Physicists were pretty confident about their model of how the universe worked, down to a time of about 1 second, where the conditions had to be right to start to form these light elements. So how flat would the universe have to have been then to explain how flat it is now? And it has to be extremely flat to, parts in 10 to a large number. And that seemed just very odd that that would be the case. So the solution to both of these problems is something called inflation.
I didn't expect that I'm going to be a cosmologist. I thought that I'm going to work on particle physics, but then unexpected things happened.
The original theory of cosmic inflation was built independently by Alan Guth in the US and Alexei Starobinsky in the Soviet Union.
Inflation introduced a new phase at the very beginning of the universe, before the formation of atoms, in which there was a sudden accelerated expansion of the universe.
Inflation would have been staggeringly brief and increased the size of the universe by a scale that is hard to comprehend and even to say. In much less than a trillionth of a second, the universe would have expanded by 100 trillion times.
And you would very rapidly blow up a space smaller than an atom to, larger than a galaxy, very, very, very fast.
This means the overall universe is much bigger than we can ever observe from our own bubble within it.
So it's a very fundamental rule in physics that nothing can move through the fabric of space faster than light. But that actually says nothing about the fabric of space itself. The fabric of space itself can expand faster than the speed of light in these theories. There's nothing to prevent that. And that's what happens during the inflationary phase. The distance between points is growing faster than the speed at which light can close the gap between those 2 points, so to speak.
But there was a brief moment before inflation began, in which the universe expanded much more slowly.
Those regions that we observe on the sky being the same temperature, they were all connected at this earlier time before the universe got ripped apart by inflation. Inflation also explains why the universe is so flat, because that expansion takes whatever geometry the universe had prior to inflation and stretches it out tremendously. So that local region that we can see today looks very, very flat. It's like if we're on the surface of the Earth now, we know the surface of the Earth is curved, it has continents and oceans, and suddenly through stretching, all we can have access to is our backyards. Well, now our backyard is going to look rather locally flat.
The original theory of cosmic inflation utilized a core concept taken from quantum theory that suggests that there can never be such a thing as zero energy. Even a random spot in the vacuum of space has quantum particles fizzing in and out of existence. In this picture of the Big Bang, the tiny and seemingly empty speck from which the universe would grow was bursting with potential energy.
So this is a strange way of producing lots of particles, lots of energy practically from nothing.
In models for inflation, the universe that would have been extremely compressed was composed of like an energy field. And it would be the stored up energy in that field that would be released, a little bit like releasing a spring. They would have this sort of potential energy, this energy that's raring to go.
This newly unleashed energy and the rapid creation of space would propel a chain reaction of bubbles of potential energy exploding.
And as a result of it, the universe does not look like one bubble, but instead it looks like bubbles, producing bubbles, producing bubbles, producing bubbles forever. It becomes a fractal. So the classical picture of the universe, which is something big and round, okay? No, it's not a big and round. It's something well, like a tree of universes growing like that.
And this mechanism, with its random fluctuations, is ultimately responsible for us being here at all.
So the idea of inflation is that all structure in the universe originated from quantum fluctuations during this hyperexpansion phase at a very early time.
If the quantum fluctuations in the Big Bang were the correct description, plus inflation, then we should have roughly the pattern of hot and cold spots that we see in the sky, and that should match with where the galaxies are today. Sure enough, they do. The current idea is gravity acts on the denser regions and stops them from expanding, pulls the material back together again to make a galaxy and then planets and stars. So we're here because of those spots in the Big Bang radiation, plus gravity, which is a pretty amazing result.
But inflationary theory, in its original form, had a fundamental problem.
This energy would sort of permeate space and would be expanding incredibly fast. And somehow you have to stop that from happening in a gradual and smoothly controlled way.
For about a year or more, many different people worked on it. Stephen Hawking and his collaborators wrote a paper saying that it's impossible to solve this particular problem.
But late one night, Andre had a brainwave.
I waked up my wife and I said, I think that I know how the universe was born.
During the summer of 1981, Andre wrote a paper on the modified theory, which he called New Inflation.
And so what Andre Linde came up with was a different mechanism for gently sort of rolling into a smoother expansion than had been come up with to begin with.
And in October, there was a conference in Moscow. Lots of brilliant people came, and one of them was Stephen Hawking. And I gave a talk at this conference, and everybody got very excited. But next day, I came to the talk by Stephen Hawking. Unexpectedly, they suggested me to translate. Steve would say one word, his student said one word, I translated this word. It was about old inflationary theory. And then Stephen said, and recently there was an interesting suggestion about how to improve it by Andre Linde, and I happily translated. And next second he said, but this suggestion is completely wrong. And for half an hour I was translating why my own theory, which I just reported the day before, why it does not work, etc., etc.
After the lecture, Andre asked Stephen if they could talk in more detail. They retired to a side room where for more than 2 hours they discussed Andre's modification to inflation.
He said something and his student would say, but you didn't say that before. And this thing continued. I ended up in his hotel. He was showing me photographs of his family and we became friends.
Hawking realized that Linde had solved the issues that were plaguing inflation. He had proposed a mechanism by which inflation could not only start, but gracefully come to an end. Andre was invited to come back to Cambridge and work with Stephen, where over the next year, they and their fellow cosmologists molded a simpler and more robust inflationary theory that became the centerpiece of Big Bang cosmology. By the late 1990s, cosmologists knew that there was some evidence for inflation, but they wanted to find the smoking gun that would tell them that it must have happened. And they were sure that it could be found in patterns within the cosmic microwave background.
If inflation happens, a likely thing to come from it is this really particular signature that we're all searching for now with our telescopes. And it's an imprint of ripples in space-time that would have been imprinted during that inflationary process.
The patterns they were looking for are called polarization patterns. But what is polarization?
Any given ray of light is a fluctuation in the electric field and a fluctuation in the magnetic field that are 90 degrees apart. And then this whole wave train is moving along the third direction. As you rotate around the direction of motion, these are other polarizations. So you have a continuous range of polarizations for each individual ray of light.
The polarization properties of an individual ray of light can tell us a story about what has happened to the light on its journey to us.
Now, most of those fluctuations we see in the microwave background, they're like a sound wave. It's a compression wave traveling through the universe.
This first, common type of fluctuation creates either a cross-like or circular pattern, which is called an E mode. But there is another pattern called a B mode, and this is the one that is crucial to finding evidence for inflation.
In Einstein's theory, you can also have fluctuations in space-time called gravitational waves, and they don't act like a density wave that compresses and rarefies. Instead, they squeeze space in one direction and stretch it in the other direction while they're propagating in the third dimension.
Those fluctuations have a very, very specific signature.
They will have imprinted a particular form, a particular swirliness, actually.
And if we could detect this pattern of swirling, twisting polarization in the microwave background, that would be perhaps indirect evidence that inflation took place. If it could be observed to be truly cosmological, not caused by some systematic error in the instrument or in the galaxy or something else, that would be as close to what was called smoking gun evidence that inflation took place.
In 1996, the European Space Agency, ESA, started planning a space mission called Planck to map the cosmic microwave background at very high resolution. In the sky maps you will see the different colors show the temperature variations. Blues and yellows are hottest, through to greens and then red for the coldest areas.
Initially, we were not planning to measure polarization when we first started out with the project.
Planck's prime mission was to do the ultimate job measuring the temperature variations in the microwave background.
People had not really realized how important and how much information polarization signals would carry. So it was not the primary goal.
A separate project from around the same time called Boomerang didn't go into space, but used balloons to make high-sensitivity observations of the CMB.
My last year as a graduate student, I worked on developing new technology detectors for Boomerang. Now, the detectors that were developed on Boomerang turned into the detectors on the Planck satellite, and they were developed here at JPL. In the midst of Planck's development, the science team got more and more interested with polarization measurements.
So I was also a postdoc at the California Institute of Technology. I was really fascinated by building a telescope that was only sensitive to the polarization in the microwave background.
Myself and Brian Keating, we came up with an approach that we call B modes or bust.
We proposed to the Caltech president at the time to get some seed money.
We said we're going to look for this inflationary gravitational wave signal to look and see if we can see it, and build an experiment that's just tailor-made to do that one thing and do it really well.
We would have loved to take it into space, but spaceborne experiments will cost you anywhere from 100 to 1,000 times more than their ground-based equivalent, and we believe we could do it from the ground if we went to an exquisite site like the South Pole.
Brian, Jamie, and their colleagues established BICEP, Background Imaging of Cosmic Extragalactic Polarization.
I started working on it full-time, 2007, 2008.
The stage was set for a battle between two very different missions, both sharing closely related technology. But for the Planck team, they still did not really believe that BICEP was a competitor.
Within the Planck community, we were not really all that concerned. What BICEP was trying to achieve was quite a different thing, using quite a different approach.
The really novel thing about BICEP is the telescope.
So we're looking for swirly patterns in the polarization on scales several times bigger than the full moon. Now, you don't need a very big telescope to do that.
A telescope of 25 centimeters or so would be just fine. And actually that brings a huge number of advantages, because I can take that small telescope and I can spin it around to take out any polarization that's in the instrument. It's really hard to do that with a large telescope.
The small size of the BICEP telescope also makes it easier to cool. The ancient light of the cosmic microwave background is now extremely cold. So in order to see it, the telescope itself must be kept very cold.
I can cool that whole telescope down to 4 degrees above absolute zero. And that's very hard to do with a large telescope. The first generation of BICEP used these kinds of detectors we developed for Planck, called a bolometer. And the basic idea is you take something that absorbs, in this case, millimeter wave radiation, and you stick a sensitive thermometer to that absorber. And if any radiation hits the absorber, you measure the increase in temperature using the thermometer.
The BICEP experiment is located at the Amundsen Scott South Pole Station in Antarctica.
The South Pole is flat, it's featureless, it's cold, it's barren, it's dark. Literally 6 months of the year, the sun is below the horizon. And we pay one person to sit there for the next 9 months of his or her life, but we call that person a winter over. And we always joke, we're gonna pay you $75,000, and all you have to do is work for one night, because that's all they'll be there for. So it would sit there at the South Pole, and it would scan back and forth for years on end, accumulating data, storing the data, we're testing it, we're analyzing it, we're looking for artifacts. BICEP-1 was created in 2001, and we deployed it in 2005. It took data from 2006 till 2009. We then decommissioned it to make way for a bigger, better instrument called BICEP-2.
Those first 3 years really showed that the method worked really, really well. Meanwhile, much of the field was struggling with larger telescopes to do these kinds of measurements.
After 13 years of careful development, the European Space Agency was ready to launch the Planck spacecraft in May 2009.
I was very happy to be part of the Planck collaboration. I joined when it was about to be launched.
So basically, you can think of Planck as a camera that has a lens of about 1.5 to 2 meters in diameter. It has an array of about 50 detectors or so.
While we were pleased with the devices on Planck, BICEP didn't have as much sensitivity as we ultimately wanted. We needed to increase the detectors from dozens to hundreds to thousands to tens of thousands. And the way to do that is using the same methods that we use to make computer chips. You want to lithograph the entire structure and reproduce them many, many times. And in fact, you don't want to just reproduce the bolometer, you want to produce everything about it. How it couples to light, which we use a printed antenna, and how we select the frequencies. All this is just lithographed on the device itself.
So you build an instrument, you measure the sky with it for a few years, you build more detectors, more sensitivity, more data, so you can improve the sensitivity faster. So that's been the pattern. There was BICEP-1, then there was BICEP-2, then there was Keck array. But basically, it's just continual arms race of improving sensitivities.
Between 2010 and 2012, BICEP-2 collected thousands of scans of the sky.
BICEP was observing a very small part of the sky with as much sensitivity as they could. They chose the patch of the sky which they thought would be the cleanest possible.
During the same period of time, ESA's Planck spacecraft revolved once every minute, slowly scanning the entire cosmos over the months.
The measurements that we take, they do not reveal things instantaneously. The data take years to acquire. They can take a year or more to analyze.
We have 4 scientists representing the BICEP2 collaboration. John Kovac.
People have a slightly ivory tower view of science sometimes. It's like we all sit in the common room smoking our pipes and being great chums with each other. Science can be fiercely competitive. People's careers depend on the results that you publish ahead of other people.
So the theory of cosmic inflation, which attempts to explain the start of the Big Bang itself, predicts that the early universe will contain a background of gravitational waves that produce patterns of polarization called B-modes.
Suddenly there was an announcement by the BICEP2 team claiming that they had observed primordial gravitational waves.
Today we're going to be reporting the detection of B-mode polarization as seen by the BICEP2 telescope that matches very closely the predicted pattern.
This was big news in our community, and so many of us watched the results together.
It's amazing.
You talk about it being thrilling. Maybe it was in a way, but it was also terrifying.
Up here today are the co-leaders of the BICEP and Keck Array series of
well, I think the first reaction was, wow.
Major collaborators that you see in BICEP2 over the past.
Because it was presented as a clear-cut case.
UC San Diego, Brian Keating's group there.
There are considerable challenges to separating the E modes and the B modes accurately enough. We had to develop new mathematical techniques to allow us to do that. When we applied those techniques, we started to be able to see a B mode detected with statistical significance for the first time. And this was, of course, tremendously exciting. It was what we had been trying to do for all of these years.
Pattern is very distinct. However, the signal is very small.
And they said, we have found gravitational waves. This is yet another confirmation of inflationary theory. Everything was great.
We felt that the polarization pattern on the sky was real.
As Clem Pryke would later say, we, instead of seeing a needle in a haystack, we observed what was later he called a crowbar in a haystack.
Okay, so this is the actual polarization pattern map as measured by the BICEP2 telescope.
Think of it as little sticks indicating the direction and the magnitude of the polarization.
The most reasonable interpretation is that it is gravity waves written in that microwave background pattern, and those gravity waves come from the inflationary epoch at a tiny, tiny fraction of a second after the beginning.
The BICEP team had made an announcement that suggested that the holy grail of signals had been found. One that would show for certain that inflation had occurred and that the Big Bang model was correct. But there were troubles brewing.
But if other people have other data and they can go in and say, actually, we don't see the same thing as you, that's the risk you run.
As you may have gathered, it seems traditional now that each experiment is very secretive about what it's doing. As soon as people started to look at the paper and at the details, they realized that maybe there are some issues here.
Now, we had only measured the sky at one frequency, basically where the CMB is brightest. Now, it's possible that we would have contamination from our own galaxy, from polarized dust.
The issue is that we had the means, Planck had the means to measure the dust part of the signal.
There were no measurements available to our team at the time of the brightness of polarized dust in these faint regions. The Planck satellite team had this data, but we didn't have access to it.
The BICEP team thought they had an agreement with ESA that the Planck team would provide them with data that would show the dust contribution to the BICEP signal.
But it's not the way it played out in the end.
We did ask, and they did not provide us the data. That could be A, they didn't have it. B, maybe they did have the results and they were bluffing. C, this wasn't something that they could agree upon on our time scale.
Well, of course, it was certainly not about destroying anybody or any group. It was about getting the good result, right?
Well, so the first thing that happened is the Planck team put out a paper on the polarization in the diffuse sky, including our region. And it showed indeed that the polarized emission from the galaxy was bigger than we had assumed from models.
The signal that we saw turned out to be dust emission. The thing that clears up scientific disputes and uncertainties is data.
In order to get a clean understanding of the problem, you needed to use both sets of data. You couldn't do it with Planck only, you couldn't do it with BICEP only. And so we very quickly decided that we had to work together with their team.
The two teams joined forces, and together they published the results of what had happened in this remarkable story. They jointly told the world that BICEP had not yet found evidence for inflation.
Well, I thought, oh man, that must hurt. That was tough luck for them. They were too eager.
It's a bit embarrassing, perhaps, but I think being a skeptic about any result and getting independent confirmation, that's how science works. And, point here isn't how I feel. The point is, how do we get to the best result?
I don't think I was particularly sorry for them, in the sense they did a wonderful job. I was sorry because it wasn't true, because it would have been scientifically much more exciting to actually have access to that signal, and therefore to inflation and to a new part of knowledge in the universe.
It is widely acknowledged that the BICEP team did great science, but at this time, they were fooled by the galactic dust.
They made a mistake, but on the other hand, they were the first to come to the verge of possible discovery, and they're still the best.
Theoretical scientists like Andre need experimental scientists like Jamie, Brian, and Clem. A scientific theory is of limited use unless an experimenter can come along and prove that a theory is correct. And this is the story of the Big Bang. Edwin Hubble proved Lemaitre right, that the universe must be expanding. Penzias and Wilson proved the theorists were right when they found the cosmic microwave background. But as we shall see, finding evidence for inflation is still the key objective.
I think the consensus today in the community is that inflation is the best candidate for the phenomena at the early part of the universe, and so I think we should pursue this, no question about it.
I'm involved in a project called the Simons Observatory, which is building a set of telescopes that are going to be in the north of Chile.
So the Simons Observatory is a large collaboration spanning all 7 continents of approximately 300 individual researchers and about 45 institutions.
If you can't be in space, the 2 best sites are Chile and the South Pole for looking at this CMB radiation, is because they're very dry.
BICEP is also continuously pushing the envelope on their experiments in the South Pole, and both teams plan to build a healthy competition between them.
So their goal is to compete with us head to head, and we'll see who does the best.
The goal is to reach similar sensitivity to this radiation and to these gravitational waves from both of these locations on Earth. I see it as being important to have 2 complementary approaches to such an important potential discovery.
I think it's very good that people are collaborating and sharing information. I think that's the way science ought to work.
Best part about it is that no one can do it alone. One of the powerful lessons of BICEP 2 is that it will take the village of all of cosmology, that we will rely on the confirmation of sometimes our competitors.
Looking down the horizon, we can perhaps envision a day where there'll just be one experiment.
So there is a concrete plan in the works for the ultimate ground-based CMB experiment, and it's being called CMB-S4. The objective is to make observations from both South Pole and from Chile with apparatus somewhat similar to the current experiments, but just a lot more of it. And so it's a kind of a mega experiment.
I'm sure that all the work that has been done so far, including the one from BICEP, will help in reaching that final goal.
The Big Bang Theory attempts to answer the biggest question anyone can ask. Where do we come from? The theory has passed many challenging tests, and it is the best description of how our universe began.
We have to be prepared that all these dedicated efforts may ultimately fall behind the unknowable screen.
It may be that there is simply a limit to how much one can know about the earliest moments of the creation of the universe.
The way I say it is, you imagine in your mind running the universe backwards to while everything is compressed and compressed and hotter and hotter and hotter, and when you run out of imagination, that's what you call the Big Bang. And we may push the imagination a little farther, but eventually you probably still run out of imagination.